All right, let's have a look at the yield line theory. So this is the street sign. If I get close up to it, so obviously there's a separation between the base plate and the concrete pavement, and you can clearly see that yield lines that is forming around this welded uh, lines here. But also you get to see that there's a little bit of separation between the base plate and the pavement, and the same as the other end. So that means the bolt gets stretched, elongated a little bit. So this is the typical mode 2 failure of the yield lines. But mode 1 is you don't, for the mode 1, obviously you don't get this separation for the bolt. Your bolt is still secured to the pavement, to the concrete, or to the boundary conditions, or whatever you might be. You only got the flange yielding. That's your mode 1. And the mode 2 is a bit of combination of the flange yielding plus your bolt elongation. So this is a combination of the two. So in this case, you can see this street sign here is a typical mode 2 failure. And the mode 3 is when you have a very strong base plate. Your base plate is not able to yield, but it's kind of stretching your bolt and fracturing your bolt. So this is not ideal mode of failure. It does not give you any warnings. But mode 1 and mode 2, they're targeted design failure mechanisms. It gives you enough warnings saying, hey, this is probably time to replace or remediate your structure. So this is the yield line theory. It helps us to design your base plate, the bolt, and also, especially during capacity design, you want to choose your failure mechanism. So let's have a look at the. Okay, hang on. Before we looking at the example, let's dive into a little bit of mechanics in here. So this is the yielding along this line. So there's important stuff. It's called the LEFF. That is the T-stop, the length. You need to pick your yield line. So when it is a curved one, but if you're looking at it, if you imagine this is a straight line, you unfold it, so this line becomes a straight line. So the longer straight line you get from your failure mode, the better your yielding capacity your base plate will be. So this is why when people getting using this stiffeners to stiffen up the edges, that's why you can mobilize more yield lines. Imagine without this stiffener, your yield line would be goes around like that. It obviously is shorter than having a stiffener in the middle, breaking it up, so you can have more and longer yield lines. So more yield lines, the better. And the second thing is there's a mechanics associated with it, which is the because you are yielding your plates, base plates, right? So your base plate yielding, let's say your plate stress is a 300 MPa. That's your yield stress over the plate. Your plate has got a length and got a breadth, so the TBT. So basically your stresses of the plate yielding that is going to have to be your you have a moment and divided by your section modulus. And your section modulus is known because you can get that from BD squared over 4. That's your section modulus. And then you can get your moment. That's your plastic moment of your base plate. And your sigma is known. You can choose a 300 or 350 steel, whatever it might be. And you can get your MP. That's your plastic moment. From the moment, because you can see that your center line of the boat to the edge of the yield line, that is your lever arm, right? So your moment and the force P, resistance of force is going to be your P times your lever arm. That's called L times the lever arm gives you the moment. So that's how this three modes of and the three modes of failure, that equation is derived. So the moment, the plastic moment divided by your lever arm gives you force, resistance force. The same thing. The second mode is is your yielding of the plate, this first component, yielding of the plate, plus the elongation, the tensile strength of your bolt, NTF, that's the bolt strength. We are using M36 bolt, the tensile strength is 541 kilonewtons, and divided by a longer lever arm, M plus N. So M plus N, that's the mode 2, a longer lever arm, and mode 1, smaller lever arm is only M. That's why your first mode, your M is the lever arm. So, and then the third mode is just purely the tensile strength of the boat, two boats, straightforward. So by looking at your calculations, okay, this is the example, right? Our moment demand is 200 kilonewtons. By looking at comparing the three modes, so your mode 1 and mode 2, they're quite close, you know. In the design, I would probably consider both 2 because we're talking about 700 kilonewtons. But 718 and the 735 is 17-ish difference is minor. So it could be either fail mode 1 or mode 2. So just bear that in mind. And then we need to figure out what is the tensile force when the plate is lifting up. What is the force generated there? That is moment divided by your lever arm. I will go through that. So that gives you 650 demand, and you are providing the minimum as 718 kilonewtons, which is good, which means your connection design is valid, and it's also a very ductile design. And also, just because of that, if you're using a capacity design, we make sure that the fuse is yielding, right, and make sure the steel member is intact, is okay, is protected from the yielding. So we need to use overstrength factor 1.25. You can check that in 3404, the table. And also the overstrength comes from the provided strength, which is 718, and divided by the demand, which is 150. That is a overstrength action times the overstrength factor times your design action moment is 200 kilonewtons, gives about 276 kilonewtons. And then you compare that with your section capacity, which is a 14 UB54. That's a 304. That's more than the demand. That means your design is valid, is okay. So yeah, just to summarize the yield line theory. First of all, you should be able to pick the correct and effective yield lines. So in this example, your yield line is going to be forming around this welded region. Is going to be something like that. That is your negative yield line. Your positive yield line is going to be from the bolt that is looking looking down is forming. There's a stretch marks. This is just looking down towards the negative yield line. So the portion of that steel plate is being pulled up, and it'll be mirrored the same thing to the other side, something like that. And the important thing is the T-stop length, L effective. There's a formula to it, and in fact, there are many formulas associated with LEFF depending on what type of geometry you have. Sometimes you have a bigger base plate, you have a bolt here and a bolt here, and you might have a stiffeners here or not. So that yield line is forming around here. So in this case, you have a different formula for your LEFF. So, but for me, sometimes I do estimations. I do because from the center of the bolt to the edge of the yield lines, that's M. That's that value here. And from the center of the bolt to the edge, that is N here, or you can say E. All right. So in this case, what I'm assuming is I'm going to say, hey, I'm going to have a length M plus N, that is 125. And that'll be, I'm assuming 125 on the other as well. And for this bit here, I'm saying my bolt is 36 mil diameter. I'm going to times 1.5. That is the edge distance, the minimum. I'm going to times 2 of them. That gives me about 350 something, 58 something. So it's roughly it's close. It's not 100%, but it's close. But just saved me time to go to look for what is the formula for the LEFF, and now I'm going to use that. I'm overestimating uh my my plastic moment. I'm overestimating that. That'll be increased a little bit, increasing, and then the rest of them are also, it's going to mode 1 and the mode 2, the resistance, it will be increasing. But you can check it as long as it's not too far away from, if you get like a 988 or something, 990 something, that's quite close to your mode 3. You might go back and check, hey, what's the actual LEF, just get it accurate. But sometimes when I just do a quick check, and to find out, this is about a 700, and the Mode 3 is about a 1000. Okay, that's about 70% of that. Okay, so my design is valid. It's going to perform a ductile yielding mode. So I'm okay with that. So yeah, that's the yield line theory. A bit of quick run through. So thanks for watching.